Hello students, and welcome to lesson 5.08 dealing with colligative properties. First, we do have some common core standards that we are going to address as we go through this lesson. If you'd like to read these in more detail, you can go ahead and pause the video at this point and read over these. You can also locate these in your course under course information and then click on standards. For this lesson, our main objective is going to be explaining how the amount of solute affects colligative properties of the solution. So what are colligative properties? Well, first let's just talk about an example, a real world example, that if you've ever lived in the northern part of the country, you have seen this in action. And you can see down here on the bottom, we got the salt truck there and some workers dropping salt on the road. And of course, again, if you've lived in the north, you know that they do that so we don't have ice on the road. Well, let's talk a little bit about the chemistry behind that. When you add salt to the water, you're actually lowering the liquid's freezing point. So, if you walk through this explanation here, when it gets, if we were living in those type of places, we add salt to the road, that lowers the freezing point. Okay, as a result, and actually it's down here a little bit, there we go. All right, as a result, that as the temperature starts to drop, instead of the water on the road freezing at, say, 0 degrees Celsius, it's now going to freeze at maybe, -4 or -6 degrees Celsius. As a result, instead of becoming ice, it will stay in liquid form. Now, of course, if it drops, temperature drops way down too cold, then obviously it's not going to have any effect. But generally speaking, the temperatures that we do have, the salt is enough to keep it in liquid form and not change it into an ice. So that's why we add salt to the road. It's also why we put antifreeze in the car engine. The solute allows us to lower the freezing point so the car engine doesn't freeze in the winter. Okay, so there's many real world examples of colligative properties. And of course, the one we just mentioned here is freezing point depression. So some terminology here that we need to look at first. So a colligative property is simply a property of a solvent that depends on the number of solute particles dissolved in it. It doesn't matter what the solute particle is. It could be sugar, it could be salt, it could be another liquid. It doesn't matter what the solute is. All that matters is how many particles we're dissolving in that solvent. So it makes sense then to say this, that the more solute we add, the more the colligative property changes. So using our real world example a moment ago with the salt on the road, if we add more salt, then it's going to have a greater effect, so it's going to lower the freezing point even more. So if you just sprinkle a little bit of salt, it'll have a small effect. If we sprinkle a lot of salt, it'll have a greater effect. And that's true for all colligative properties. So we want to count, if you will, the number of particles that are involved. The three main examples that we're going to look at are vapor pressure lowering, boiling point elevation, and freezing point depression. And the last one there was the one that we were just talking a little bit about with our real world example. Alright, so let's go ahead and look at those three in a little more detail. First off, vapor pressure lowering. Well, we got to first define vapor pressure. Alright, vapor pressure is simply the pressure exerted by the vapor particles that evaporate from a liquid typically, or it could be a solid, in a closed container. Alright, so if you look down here on the bottom, you can see we've got a picture. The left side, we have the pure solvent, whatever it may be, and your solvent can be anything, it doesn't matter. And you can see that we got the large solvent particles here in solution, and then there's a small space in the top here between the liquid and the cover. And you can see that there are small vapor particles up in there floating around. Well, back in earlier module 5, we talked about how pressure is a measure of how often these particles collide with the wall of the container. So we can measure the number of collisions with the wall of the container, and that is our pressure. Now, because it's coming from the vapor that was released from the solvent, that's why we call it vapor pressure. Okay, so we got a certain level of vapor pressure in here from those particles. Now, if you add a solute to it, okay, over here on the right side now, we've added some solute, and you can see how what happens is the solute along the surface here, in a sense, kind of acts like a blockade in a way, and gets in the way of allowing the solvent particles to go into the vapor form. All right, now there's a couple reasons for that. First, because they're just simply in the way. All right, they can't get around those particles. The other reason is there is attractive forces between the solute particles and the solvent particles. Because they are attracted to each other, instead of leaving the liquid and going into the vapor form, they want to stay right where they are, connected with the solute particles. So as a result of both of those things, we end up with less particles going into the vapor form. And of course, if there are less particles, going back to kinetic molecular theory, right, less particles means we're going to have less collisions with the wall of the container. So we're going to have a lower vapor pressure. All right, so again, by adding a solute, we're going to lower the vapor pressure because we have lowered the number of particles in the vapor form. Okay. Now, just a little side note here. As you increase or decrease temperature, you also are going to change the vapor pressure. All right. As you increase the temperature, you're going to increase vapor pressure. Just like when we did our gas laws. Increase temperature, increase pressure. Okay, and really it's the same reasoning back when we did 5.03. Okay, by increasing the pressure, or the temperature, these molecules are moving more rapidly, and because they're moving more rapidly, they're going to be able to escape the liquid phase easily and go into the vapor form. So because you're going to end up with more vapor particles, you're going to have an increase in the vapor pressure. Okay, so that's just a little side note there. Again, the great example of that is, if you take a can of soda, have it in the fridge versus leaving it outside on the sidewalk for a few hours. The one on the sidewalk, if you open that, it's going to fizz all over the place because it's been outside, it's been warmed, so the molecules are moving faster, so there's more vapor pressure because there's more molecules in the vapor form. The second one actually ties into the vapor pressure one, and that is boiling point elevation. So again, let's first define boiling point. Boiling point is simply the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure of the surrounding air. Okay? So again, the vapor pressure equals the atmospheric pressure. That's where we hit the boiling point. Prior to this, we define boiling point as the temperature at which it changes from liquid to gas. Okay? The reason it changes from liquid to gas is because those pressures are now equal to each other. All right? So, since vapor pressure of a liquid is lowered by the addition of the dissolved solute, then the solution will have to be heated more to get it to a higher temperature so that the vapor pressure equals atmospheric pressure. Okay? So again, over here, in our illustration, we've got our pure solvent, right? And those solvent particles go into the vapor form, okay? And again, it's at a certain boiling point, right? And you can see over here on the thermometer, it's roughly right about here, kind of underneath this one dot right here. That's the boiling point of the pure solvent. Now, because we add solute particles, remember we're going to have less in the vapor form. Well, to get the pressure that these particles are pushing back towards the top here, to get that pressure equal to the pressure of the atmospheric pressure pushing down on it, we have to have the same number of particles. Just like over here, we had a certain number of particles pushing up to make it equal with the atmospheric pressure. Well, over here we got to do the same thing. Well, the only way we can get to that point is to increase the temperature. You can see that the boiling point goes all the way up to here now. Alright, so by increasing the temperature, the particles are moving faster. So even though there's solute interfering, we're eventually going to get enough particles into the vapor phase that we have a vapor pressure equal to the atmospheric pressure. So as a result, the boiling point is going to go up. Okay, a great real world example of that would be, cooking pasta. Many of us put salt in our water when we're cooking pasta. Most people will say they are doing that for flavor. And yes, salt does give it some flavor. But another reason, probably the bigger reason, is that it is actually causing the boiling point to go up. So now instead of cooking your pasta at 100 degrees Celsius, you may be cooking it at 104 or 105 degrees Celsius. So if you're cooking at a hotter temperature, you are now going to decrease your cook time. So that's the chemistry reason for adding your salt to the boiling water when you're making your pasta. All right, and then the last one is freezing point. Okay, freezing point is the temperature at which a liquid undergoes a phase change from liquid to solid. Okay, now to do that, again, going back to our kinetic molecular theory, as the liquid particles are slowing down, they begin to have attractive forces between them, and at some point they're going to slow down enough that those attractive forces take over and cause it to form the crystal structure of the solid. All right, and of course, we'll use water as an example. That happens at 0 degrees Celsius, is where the liquid water get in a line, if you will, with one another, and they have those intermolecular forces holding them in place. Again, remember, they are still wiggling, but they're held in fixed positions. That is when it's a solid. Now what happens is when you add a solute to that solvent, the solute particles disrupt that process. As the solvent is trying to make the crystal structure, the solute is in the way. Okay? If you have a group of people that are trying to, maybe form a chain, to do like just some type of connection, group activity or whatever, and there's a bunch of people in the way, you're trying to do it in a crowded mall or something, or there's a bunch of people in your way, it's going to be more difficult to do that, and it's going to take longer to get it accomplished. Well, the same type of thing is happening here. As the solvent particles are trying to make those connections, the solute particles are in the way and disrupt that process. So what happens is it's going to cause the temperature to continue to drop until the solvent particles can finally make their connection. So now instead of having water as our example freezing at 0, it's now going to freeze at maybe -4 or -5. Okay, it's going to be a lower temperature, again, depending on how much solute particles we add. All right, so those are our three: vapor pressure lowering, boiling point elevation, freezing point depression. Now, to actually do the quantitative portion of this, we have to introduce a new term here, and that is molality. Earlier we talked about molarity in lesson 5.06. Here we're going to talk about molality. We just changed the letter there. Molality is the concentration of a solution expressed in moles per solute, or excuse me, moles of solute per kilogram of solvent. So if we compare the two here for a second, the one that we learned earlier, molarity, capital M, moles of solute per liters of solution. Molality, we use a lowercase italics or cursive looking m, equals moles of solute divided by kilograms of solvent. Now the reason that we change it is because, remember, we're talking about particles when we're doing colligative properties. Molarity doesn't do particles for us, it does volume. So we need to do particles. Well, mass does particles for us. So that's why we have to change our formula just a little bit here to get something that we can actually use when we're talking about colligative properties. So this is the one that we use when we deal with colligative properties. Moles of solute per kilograms of solvent, and that gives us what's called molality. So of course, if we have a formula, we need to do some practice problems to make sure we are able to use that formula. So let's look at this first one here. What is the molality of a solution in which 15.0 grams of NaCl dissolve in 500 grams of water? All right, so going back to our last screen, remember our formula is molality equals moles of solute over kilograms of solvent. Now we are given grams of solute in grams of solvent. So we need to do some converting before we can actually plug into the formula. Our grams of solute, the 15 grams, needs to be changed into moles, and our 500 grams of water needs to be changed into kilograms. So let's do the first one there. We've got 15 grams of the NaCl. Alright, and remember from all that we've learned about moles and grams, to get from grams to moles, we need the molar mass. So we go to the periodic table and look up our two molar masses. For Na, we have 22.99. For Cl, we have 35.453. So we add those together. And again, we don't have to multiply by anything because it's 1 Na and 1 Cl. And that's our molar mass. Now remember, to get our units to cancel out, we would divide by that. So we got 58.44 grams per 1 mole. All right, and we put the grams on bottom so we're canceling out our units. So 15 divided by 58.44. And that's going to give us 0.2567 moles of NaCl. Okay, so that's our first part of the formula. Now for the second part, we started with 500 grams of water, and we need to get this into kilograms. Okay, so this goes all the way back to Module 1 and the metrics. Right, we always have to know our metrics. And remember that there is 1 kilogram for every 1,000 grams. Right? Kilo means 1,000. So we put the grams on the bottom to cancel out our units, and that gives us 0.5 kilograms of the H2O. Alright, so now we have what we need. We can just go back up to our formula here and just plug in our values. Okay, so I have on top 0.2567 moles of the NaCl. And then on the bottom, I have the 0.5 kilograms of water. So our final answer, again, making sure we use the right number of significant figures. We'd have 0.513, and we use lowercase m to represent the molality of NaCl. Alright, so that's how we solve for molality. Again, the main thing is making sure you get everything into the correct units, just like we did for molarity, and then just divide those two to get your final answer. Alright, now let's go back to some qualitative stuff and look at when we have ionic solutes. Alright, when you take an ionic compound and you dissolve that into any solvent, it's going to break up into positive and negative ions. Alright, this is going back to the dissolving process that we talked about earlier in Module 5. So those ions then get surrounded by the solvent particles. So if you look down here in the illustration, we started with NaCl, which is just salt, and when we place it in water, we'll say, is what we typically dissolve it in, the ions break apart. So you can see we've got positive ions and negative ions, and they're going to get surrounded by the water, and we now have NaCl dissolved in the water. Okay, now of course, just like with any solution, those ions are free to move about in the solution, which does allow them to conduct electricity. Okay, that is why they are called electrolytes. A substance that when you dissolve it in water conducts electricity. Again, this was back in 3.06, I believe, was the lab where you took some salt, you tested it for conductivity in the solid state, and then the liquid state, and then the aqueous solution state. And this right here is the explanation as to why it conducts electricity, because you have these free-flowing electrons, or excuse me, ions. So when you put some electricity in there, they are going to transfer that electricity throughout the solution and then continue the circuit for you. Alright, so of course ionic solutes, as we just said, are electrolytes. Now the thing here, though, that you need to notice is that the number of moles of solute is really the number of moles of ions. Okay, we take NaCl, which is one compound, but when we dissolve it, we end up with two particles, Na plus and Cl minus. So when we're dealing with ionic compounds, and remember for colligative properties, we want to know the number of particles in solution. Okay, we don't care what they are, we just want to know how many particles there are. Well, in this case, for every NaCl that is dissolved, we actually will have two particles in solution. two solute particles in solution. So when we deal with ionic compounds, we have to take this into account when we're talking about colligative properties. All right. So let's kind of apply this idea here. If we have 1 mole of strontium chloride and it's dissolved in 1 liter of water, and I have 1 mole of sugar also dissolved in 1 liter of water, how will they compare in terms of moles of solute particles, vapor pressure, boiling point, and freezing point? All right, well, sugar, let's start over here with the sugar. Sugar is a molecular compound. Molecular compounds, when we dissolve them in water, do not break apart like the ionic ones do. They do not form ions. So the C6H12O6 stays C6H12O6 when we dissolve it. So if I dissolve 1 mole of this sugar, then in solution I'm still going to have just 1 mole. Now for the strontium chloride, right, when this dissolves in water, if we reverse the crisscross to get our ions, we're going to have Sr with a positive 2 charge, and we're going to have Cl with a minus 1. But to get them to cancel, that's why we have Cl2. So total, we actually have 3 ions. We have 1 Sr plus 2 ion, and then we've got 2 Cl minus ions. So for this one, we're actually going to have 3 moles of solute particles. Now back earlier in the slides here, we talked about that the more particles you have dissolved, the greater the effect on the colligative property. So for vapor pressure lowering, the SrCl2, because it has 3 moles dissolved, is going to have a lower vapor pressure than the sugar. Oop. Try that again. Mixing my U and my G together there. Sorry about that. There we go. All right. Lower vapor pressure than the sugar. Boiling point, all right. So again, boiling point is 100 degrees Celsius. It's elevated, so the SrCl2 maybe goes up to 110, whereas the sugar maybe will only go up to 102. You know, and those are just random numbers I was choosing there. We'd have to actually do the calculations to determine what it would be. All right. So in this case, the boiling point elevation will be greater for the SrCl2. I'm going to abbreviate this one also, greater boiling point, and then ditto marks here, than sugar. Okay, they both will go up, but the SrCl2 will go up more than the sugar does because there's more particles there. And then finally, freezing point depression, same type of thinking. They both go down, but the SrCl2 will go down more because there are more particles dissolved in solution. So we would have a lower freezing point on the SrCl2 than the sugar. So the sugar maybe will freeze at, you know, like -2 degrees Celsius. The SrCl3 solution maybe is freezing at -10 degrees Celsius. Okay, so it's all about the number of particles dissolved. More particles dissolved, greater the effect on the colligative property. All right, so that wraps us up for this lesson. As far as what's next, well, you need to make sure you complete all of lesson 5.08. Make sure you're doing all the practice problems, clicking on all the hyperlinks, those type of things. Of course, make sure you take some great notes so you have some stuff to study with. If you're still needing assistance, you can certainly join us in the tutoring sessions that we offer. Check the announcement page on the your class to see the schedule and the link. There is a review sheet in the Student Resource Center that you can use. And for the assignment, you are going to be doing an article talking about colligative properties. Basically what you're going to do is you're going to have an introduction, you're going to have a paragraph explaining the colligative property you choose, and then the third paragraph is going to be an explanation of a real-world example for that property. And then, of course, you always want to have a conclusion at the end. Make sure you include a list of your citations, your resources, and you are supposed to use MLA or APA format when you do that. And then finally, of course, my apologies for that. And then, of course, you do need to submit the article in either the assessment tab or the gradebook tab once you're finished. So if you are ready to go, you can get those wrapped up and submitted. If you are only taking the class for regular credit, then at this point you will be able to call your teacher and schedule your Module 5 discussion-based assessment. And if you are taking it for honors credit, then we'll see you back for the 5.08 honors assignment. Hope this was helpful, and we'll talk with you again soon.